We are in chapter 5 where we are discussing shear stress. This is the second session involving shear stress and the 38th session overall. Here we discuss the variation of the stress tau Zx. We discuss shear flow in an I-beam and also in a beam of box-shaped cross-section. These were the 36 sessions covered in the first 4 chapters. We looked at background, stress and axial loads, strain, torsion, and bending. This is the second session out of 6 sessions in shear. Here we look at stress and shear flow in an I-beam and a box-shaped beam. We have earlier developed expressions for tau xy and tau xz. We earlier discussed the variation of tau xy. Here we'll discuss the variation of tau xz. We take this arrangement of loading. Two sections 1-1 and 2-2 are considered. They are del x distance apart. On the top, both sections are subjected to tensile stresses. The tensile stresses acting on section 2-2 is larger than the tensile stresses acting on section 1-1. We have separated the slice in figure 2. We further take a vertical section 3-3. The top of the flange in this figure is shown as ABCD. This small portion is shown enlarged in figure 3. This is section 1-1, this is section 2-2, and this is section 3-3. Section 1-1 and 2-2 are considered to be quite close to each other, so that the thickness of this section is of one element only. The normal stresses on the right side is greater than the normal stresses on the left side. Hence, for equilibrium, there will be shear stresses acting on section 3-3. From the unit cube, you can see that the designation of this shear stress is tau Zx. Then, as earlier discussed, there will be a shear stress acting around the corner. From the unit cube, we can see that this shear stress is designated as tau xz. By rotating figure 3, we get figure 4. We can now see the stress tau xz acting on section 1-1. The area of CDEF and ABGH are the same. The shear flow in section 3-3 is given by Q is equal to V capital Q divided by I. Q is the statical moment of the area of ABGH. Consider the underside of the flange to be at a distance y1 and the top of the flange to be at a distance h by 2 from the neutral axis. The rectangle ABGH is shown here. Consider an infinitesimal element of area dA. This element is at a distance y from the neutral axis. Then the statical moment is YTA, integration from Y1 to h by 2. The distance AB here is given as Z, so we get YZBY integration Y1 from Y1 to h by 2. Hence, capital Q is given by this expression. Shear flow is VQ divided by I, so shear flow is given by this expression. Dividing the shear flow by the thickness of the flange, we get tau Zx. Now tau Zx is equal to tau xz. So tau xz is given by this expression. We'll now vary the distance from the edge. So from the outer edge, we'll move inwards. Thus, we'll vary Z and take different sections 3-1, 3-1, 3-2, 3-2, and 3-3, 3-3. Consider the section 3-1, 3-1. The corresponding Z is Z1. We take statical moment of this small area, and tau Zx is small. As such, around the corner, tau xz is also small. Now let us take section 3232. The corresponding Z is Z2. So we take the statical moment of area of this larger rectangle. Tau Zx is now larger, and around the corner, tau xz is also larger. Consider section 3333. The corresponding Z is Z3. We take statical moment of this area, which is greater than the previous case. So tau Zx will be still larger, and as such, tau xz around the corner will be still larger. Now tau Zx and tau xz both vary linearly with Z. So the shear stress acting at section 1-1 will vary linearly with Z as shown. The shear flow in section 1-1 will also vary linearly. In figure 5b, we have shown the right portion of the beam from section 1-1. From equilibrium, we can see that there will be a vertical internal force acting on section 1-1. The force acts downwards. The fact that the force acts downwards in the web is utilized in the next slide. Here we'll discuss shear flow on the whole I section. To start with, the variation of tau xy on the axis of symmetry. Earlier we discussed the variation of tau xy in a rectangular section. The variation was found to be parabolic. The web here can be considered to be a rectangle with small thickness. So the variation of tau xy in the web will also be parabolic. If the web is thin, the variation of tau xy from top to bottom will be small. Shear stress is given by the equation VQ divided by IP. For the flange, B is higher compared to the web. So magnitude of the shear stress tau xy in the flanges are small. In the last slide, we discussed that the shear force acting on section 1-1 will be downwards. This shear force is made up of shear flow acting on the web, which is also directed downwards. We'll now look at directions of shear flow in sections 3, 4, 4, 5, 5, and 6, 6. That way, we'll be able to give the direction of shear flow for the whole I section. We give the direction in section 1-1. As earlier, let us consider this portion of the flange. We rotate it 90 degrees counterclockwise. This is an enlarged view. AD here is the free edge. The tensile stresses on the right side will be larger than the tensile stresses on the left side. So the shear stress Zx in section 3.3 will be directed as shown. So tau xz and the corresponding shear flow on face 1-1 will be directed towards the center. Now let us consider this portion. Here again, it has been rotated counterclockwise by 90 degrees and enlarged. Here, the stresses on the right again will be larger than the stresses on the left. This is section 4.4. So we can imagine that the shear stresses tau Zx on section 4.4 will be directed towards the left. That means this is the direction of tau xz in the section 1-1. The direction is towards the center. So the shear flow in the top flange is towards the center from both edges. Let us consider now this portion. The portion is rotated 90 degree counterclockwise and enlarged in this figure. This is the outer edge and this is section 5.5. In the lower flange, stresses would be compressive and stresses on the right again will be larger than the stresses on the left. So tau Zx on section 5.5 will be directed as shown. Then tau xz on the face of section 1-1 is directed away from the center. Now let us take this portion. It has been rotated counterclockwise 90 degrees and enlarged as in this diagram. The stresses are compressive and the stresses on the right side are larger than the stresses on the left side. So we'll expect the shear stresses acting on section 6.6 to be directed towards the right. Then tau xz on face 1-1 will be directed as shown. So in the bottom flange, the shear stress and the corresponding Q are directed away from the center towards the edges. So from this diagram, we can see that the shear flows. As earlier mentioned, the variation of shear stress and shear flow in the flanges are linear. From previous discussions, we understand that the shear stress tau xz and the shear flow at both these edges are zero. They increase linearly as we move towards the center line. At the section KK, which coincides with the axis of symmetry, the shear flow is maximum. The shear flow is given as VQ divided by I. To give the shear flow at the section AK, the statical moment of area of this portion, which is shaded, has to be taken. Consider MM, which is at the juncture of the web and the flange. If the shear flow at MM, the statical moment of this whole flange section has to be taken. So in magnitude, the shear flow at MM will be twice the magnitude of the shear flow at KK. If in the web the variation of tau xy is minimal, then the shear flow will be nearly constant. Consider a section in the bottom flange similar to KK. Then the magnitude of shear flow will be same as KK, but the shear will be oppositely directed. So we can see the shear flow in this section. At the juncture here, the shear flow turns 90 degree and merges. At the juncture here, the shear flow splits and turns 90 degree. Now look at the forces acting in the section. Due to the shear stress and shear flow, two equal and opposite forces will act on the top flange. Also, two equal and opposite forces act on the bottom flange. They are, however, oppositely directed compared to the top flange. The shear stress and the shear flow in the web primarily make up the internal force acting on the section. We can find the force F1 acting. It will be given by the average shear stress acting in the blue portion multiplied by the area of the blue portion. The maximum shear stress occurs at the axis of symmetry. Since the variation is linear, the average shear stress is equal to tau max divided by 2, and the area is thickness of the flange multiplied by the width of the flange divided by 2. Earlier we have dealt with shear flow in an I section. Here we deal with shear flow in a beam of box-shaped cross-section. The beam arrangement and loading is the same as some of the cases considered earlier. So there's a load acting here and there are reactions at A and B, but there are supports. We take sections at AA and BB, which are del X distance apart. For a section such as AA, this is the view of the box-shaped cross-section. In the horizontal portions, the shear stress will be tau xz, and in the vertical portion, the shear stress will be tau xy. Here, a view is given of the slice between sections AA and BB. We further consider two sections 1-1 equidistant from the center line. An enlarged view is shown in figure 3 with the stresses acting. The stresses acting on the right side will be larger than the stresses acting on the left side. So Fx2 will be larger than Fx1. Unlike the other cases, there will be shear stress acting on both sides to balance the difference. So if the difference is del F, then there will be force del F by 2 acting on this side and del F by 2 will act on the other side. Due to shear stress acting on this face, there will be shear stress acting on the faces of BB and AA. Let us now consider the sections 2-2 on both sides. Then this area will be larger and the forces Fx2 and Fx1 will be larger, which means the shear stresses and the corresponding shear flow will be larger as well. Let us now consider the sections 3-3 on either side. Then this area will be still larger, and these two forces will be higher compared to what we got for section 2-2. So the shear stress and the corresponding shear flow will increase. If we consider a section 4-4, then the shear flow will be still higher. In fact, the shear flow keeps on increasing from this axis of symmetry to the neutral axis. This is for this side. Let us now consider sections 1-1- on either side of the center line. The stresses acting here are compressive. So the direction of shear flow will be opposite to the top portion. If we consider the section 2-2- on either side, then the shear flow will increase in magnitude. So the overall shear flow variation will be as shown in this diagram. This shear flow is for section AA. Let us now consider an I-beam. If we wanted to find the shear stress at section 1-1, then we find the Q of this shaded portion. The Q and the shear stress at the edge is 0. For the box-shaped cross-section, the Q and the shear stress along the axis of symmetry is 0. So if we want to find the shear stress at section 1-1, then we consider the Q or the statical moment of area of this shaded portion. Another way is to find the Q of this shaded portion. Here these two sections 1-1 are equidistant from the axis of symmetry. Shear stress is given by the formula VQ by IB. If this method is being used to find shear stress, then B becomes twice the thickness. We have now discussed shear flow for two different cases, an I-beam and a beam of box-shaped cross-section. In both cases, we see that the shear flows, that is, their directions are such as if something is flowing. This essence often helps us predict the direction of the shear and is easier than the method of picking sections and finding out directions. In all the cases till now, we have considered equilibrium of the beam in the direction of the axis of the beam. We have then found tau yx and tau zx along the axis of the beam. Then we have found tau xy and tau xz, which are both perpendicular to the axis of the beam. We have an I section here with plates attached on the top and the bottom using bolts. We are given the moment of inertia and the area of the I section. Also, the dimension of the plates and the diameter of the bolts. We are also given the allowable stress and the spacing of the bolts. We are required to find the maximum shear force. First, we'll find out the maximum shear force and shear flow that the bolts can withstand. Using the radius and the allowable shear stress, we find out the force in the two bolts. Dividing that force by the spacing, we get the shear flow that the bolts can withstand. With the shear flow obtained, we can use the formula VQ by I to find the shear force V. Here we have found the I of the total built-up beam. So IZZ here is the I of this beam, and we have added 2 AD square for the plates. Q here is for the darker shaded portion. Equating with the shear flow earlier obtained, we can find V. As in the earlier case, here we have a built-up beam with an I section and 2 channels attached to the top and the bottom using bolts. Here we are given the shear force and asked to find the stresses in the bolts. The diameter of the bolts and their spacing are given. In this problem, we'll first look at the shear flow of the arrangement and then look at the bolts. To start with, we find out the moment of inertia of the built-up beam. So we use this formula. Here IZZ is the moment of inertia of the I section, and AD square is due to the 2 channel sections. To find V, we take half the height of the I section, add the thickness of the web of the channel section, and subtract this distance with the centroidal distance of the channel section. So we have obtained this value for D. To find Q, we have multiplied the area of the channel section with the same distance that we obtained earlier. Hence, we have found the shear flow. The shear flow into the spacing is the force that has to be sustained by the 2 bolts. So equating, we get the shear stress in the bolts. Here we have a built-up section with smaller screws on the sides and larger screws in the middle. The dimensions are given and the diameter of the screws are given. With the allowable stress and the loading in the beam known, we are asked to find the spacing of the screws. The shear force will vary along the beam for this type of loading. That would mean that we do not need to use the same spacing throughout the beam for the two different types of bolts. We first look at the shear force variation. The reactions are given, and since the loading is symmetrical, we find out the shear force till the middle of the beam. So here we have the shear force for the first 2.5 meters, and here the shear force for the next 2.5 meters. This is the shear force diagram for the entire beam. We'll be using two different types of spacing for the first 2.5 meters and the last 2.5 meter. We use the shear force as 17.5 kilonewton. For the middle 5 meter, we use the shear force as 5 kilonewton. Here we have obtained the moment of inertia of this built-up section. On the top, we have the moment of inertia of these portions about their own axis. In the bottom, we have AD square. So we have found out the moment of inertia. We'll first look at the spacing of the 6 millimeter screws. Q is 25 into 125 into the distance of the centroid of this portion from the neutral axis. For the first region, we use 17.5 kilonewton as V, and we have found out the shear flow. For the second region, we used 5 kilonewton as V, and we have found out the shear flow. We next find out the force carried by each 6 millimeter bolt. We find the spacing for the first region. So the shear force that each bolt can withstand is divided by the shear flow in terms of Newton per meter, and we get the spacing in meter. For frequency of the second region, the shear flow has changed and we get a different spacing. We now look at the 12 millimeter, that is the largest screws. The statical moment has to be obtained of this area. We obtain the statical moment of the vertical portion and the horizontal portion separately and add them up. For the first region, we again use 17.5 kilonewton as the shear force and find out the shear flow. For the second region, we used 5 kilonewton as the shear force and find out the shear flow. We next find out the force carried by each 12 millimeter screw. Here we have found out frequency for the first region. So the force that each screw can carry has been divided by the shear flow in terms of Newton per meter. And we have found out the spacing in meter. Similarly, the frequency of the second region has been found.